Welcome everyone to Guided Study Group Week 10 of Mat 141. So this week we're gonna go to the second piece of materials for final exam. Next week is going to be polar coordinates, which is section 10.3 and 10.4. And after that we're gonna have the last sections working on as a final review. And so let's get started today. So first of all is section 10.1, curve defined by parametric equations. So parametric equations is used to describe curves that cannot be written in the form of y equal to fx. Some of the curves that you usually see in this form are circles or hyperbola or ellipse, or sometimes we can have like 3D curves, especially those that need like a cycloid. It has to be represented in parametric curves, because for one of the way that you can think about it is that for each value of x, it can give more than one value of y. Say like these kind of curve, like look like this kind of curve that looks like the sine or cosine curves that you turn it 90 degrees clockwise or counterclockwise. Parametric equations is given in the form of C, like a piecewise function, with x be a function of t and y be another function of t. For the value of t is usually defined in a certain interval from a to b. So FAGA is usually defined as the initial point, and FBGB as the terminal point. So a parametric curves can be represented in many ways. Parametrization is not unique, and if you continue to take classes in 230 or 231, you will notice the fact that especially for curves in 3D or 4D or in higher dimensions, they can be represented in many different ways, and depending on which directions that you give out in the problem statement, then the curve would look slightly different in the way that you try to solve some equations. Then the directions actually make a lot of difference. As I mentioned briefly, we have the equation of a cycloid. So in this class, I wouldn't expect that you guys use a lot of it, but I remember in 230 and 231, cycloid is one of the important part where it comes to parametrization and where we learn the fundamental theorem of calculus 2. So some of the problems that you can be asked in these sections is sketch the parametric curves. So this one is just to familiarize yourself with the concept of parametric equations and how to actually visualize it in 2D. In 230 and 231 and even 232, you got to get a chance to actually graph them out in 3D and 4D. But further than that, you have simulations and software to do that, which we're not going to go too deep into it. And so to sketch the parametric curves, sometimes it's easy to sketch it out, but usually the approach is to eliminate the parameter t to get a Cartesian equation and use or we can have a table of x and y with respect to t, and we just sketch those points in 2D. In 230 and 231, when you actually use, you're not going to eliminate the parameter t, because those equations are usually not representable in Cartesian coordinates. So in that case, a table of x, y, z with respect to t will be a better choice to graph the parametric curves. Another type of question that you can be asked in this section is find a Cartesian equation or find a Cartesian representation of the parametric curve, or vice versa. So finishing this section, you should be able to go back and forth between these two forms. Of course, there are some parametric curve that cannot be represented in Cartesian coordinates, but in this exam, that is going to be possible, and so you have to be able to go from parametric curve to Cartesian equations. Let's go to the first example. Obtain the Cartesian equation for this piecewise functions or this parametric curve. And so the approach that I say, at least in 141, is that you try to eliminate t and put everything in the form of a regular y equal to fx function. So first of all, let's try, we have x equal to 2 minus t, y equal to t squared plus 4t, with t going from -4 to 1. And so let's first of all eliminate t. So t is going to be, from the first equation, we have x is 2 minus x. And so when you plug it back into the second equation, we have 2 minus x squared minus plus 4, 2 minus x. So if you do the algebra, we have x squared minus 4x plus 4 plus 8 minus 4x. And so we have x squared minus 8x plus 12. So that is the Cartesian equation for this part. We also have to identify what is the terminal point and initial point in xy coordinates. So when t, we have t, x, and y. Then we have -4 and 1. So for x is going to be 2 minus t is going to be 6. And then that one is 16 minus 16 is 0. And then for 1, we have 1 here. And 1 plus, that's 5. And so the 2 points is, this is going to be the parabola. Because if you look at this one as the quadratic equations, it doesn't have the form of x squared over a squared minus y minus or plus y squared over b squared equal to some constant. If it's in that form, it's either a hyperbola or ellipse. But in this case, this one only have y equal to x squared something, so it's a parabola. And so it's the parabola of y equal x squared minus ax plus 12. And so we also have, it's going from 6, 0 to 1, 5. And so that's the answer for the example 1. We also have the second part where we come to sketch the curve. So you can either choose to have a table of t with respect to x and y, and then just graph all of those points, or we can graph it with respect to just t alone. So let's give this the, okay, so we have the points is going to be, so in this case, I'm not gonna do the txy table, but I'm gonna put it in the form of a parabola, which is easier to visualize. So we have x squared minus ax plus 12. I can rewrite this as x squared minus ax plus 16 minus 4, which is going to give us a complete square here, which is x minus 4 squared minus 4. So graphing it out in 2D, and we know that the initial point is from 6, 0 to 1, 5. So we have x, y, 0. So we're gonna go from 6, 0 so this is 6 to 1, 5. This is from here. And so if you graph it out at 4, this is 1, 5. At 4, it will be -4. So when x equal to 4, you plug it in, you're going to find that y equal to -4. And so just continue with a few more points. You're going to have here to there. And so that is the curve that we're talking about. Remember, in parametric curves, you have to specify initial point, terminal point, and directions. So that's all I have for 10.1. It's mostly just to introduce us the concept of parametric curves. 10.2 is where we actually kind of use what we've learned so far, like differentiation of using parametric curves, horizontal and vertical tangent, and also use a second derivative to check for concavity of our curve. We also have area under a curve, which is big F of x, as we say is the antiderivative from A to B. So let's start with differentiation of parametric curve. As normal, it's just geometrically, it means that it's the slope of the tangent line of the curve at one point. And we can find that it's defined as dy over dx. We can find it by dy over dt divided by dx over dt, with dx over dt different from 0. We also have horizontal tangent, and it is defined as where you have dy over dx equal to 0, or the slope of the tangent be equal to 0. And vertical tangent. Vertical tangent, we need dy over dx to be does not exist, or dx over dt equal to 0. So the denominator is 0. That's how you get the entire fraction of dy over dx does not exist. Finally, as part of Math 141, where you learn about indeterminate form of limits, that's where you use, if you have, in the case that you have both dy over dt and dx over dt approaching 0 or infinity, at x approaching a, then you have to find the limit of x approaching a of dy over dt divided by dx over dt. And this is where it comes back to the material of midterm 2, where you have indeterminate form of limit and use L'Hopital rule. But hopefully in this exam, it's not going to get that complicated. Some applications in 230 and 231 at least, and I think it's the very practical applications of parametric curve is where you use it to model the path of projectile motion, or in the case of cycloid or like a spiral, it can use in 3D modeling or in any kind of motions like physical motions or motions inside a centrifuge. So so parametric curves is used to model the path of projectile motion, and the calculus of this kind of equations will allow us to determine these kind of slope and kind of like the geometric features of the curves. In the motion, we can also use, so x and y are the coordinates of the, say, an object at some point, but dx over dt and dy over dt, with t be the time, will be the horizontal and vertical velocity respectively. Second derivative, as we learned in midterm 2, is going to be the one used to determine the concavity of the curve. And finally, when we talk about area under the curve, so as we learned in Math 140, integral is where we talk about the area under the curve. And so if a curve is traced by x and y, be ft and gt, with t bounded between alpha and beta, then the area under the curve can be substituted into parametric equations as is defined. It's the integral from alpha to beta of gt multiply f prime of t multiply dt. And we're going to see that clearer if we come to the example. And I mean, again, this part of the area under the curve would not be a very big concentration of the final exam. But in 230, if you proceed with engineering or science major, then it's going to be a major part. Some problems that can be asked: find the tangent line of the parametric curve at some point or given t. Figure the concavity of the curve using the second derivative. Find the first or second derivative of parametric curve straightforward. Find the area under the curve using the formula as given, and find the points of horizontal or vertical tangents on the parametric curve. So let's see the example. Okay, let's go with example 2. Find the tangent line to x equal to that piece y functions. And so we have I always ask you guys to define what is the general function of a tangent line. It's y equal y prime at x0, x minus x0 plus y0. Now let's find what is the derivative here. Dy over dx, which is also y prime x. We have is going to be dy over dt divided by dx over dt. So this one we have negative e to the negative t, 2 cosine t minus 1 over 2 square root of t plus 1. And so we need to find the slope of y prime of x0 when t equal to negative 1. So y prime here, when we plug t equal to negative 1, we're going to have negative e to the 1, negative 1, divided by, excuse me, give me a second, I have to figure this one out. Okay, cool. Not t equal to negative 1, when x equal to negative 1. But when x equal to negative 1, we need to find the value of t to plug it in here. So when x equal to negative 1, we have 2 sine t minus square root of t plus 1 have to be negative 1. And so solving this algebraically is going to be really hard. But since you guys have a multiple choice exam, we can do guessing number for this. As long as we can prove the fact that the function only increase or decrease on the interval that we're given, which is t bigger than or equal to negative 1. So you can either choose to find the derivative of this and prove that it's always positive or negative on the given interval, and use the intermediate value theorem to prove the fact that it has at least one root, and then the mean value theorem to prove that it has only one root on the interval. But that's going to get too complicated. It is what required in the written exam, but in the multiple choice exam, we can do guessing of number. And so we're going to have just guess like numbers like 0, negative 1, power 2, or those kind of stuff to make sure that we get the number. Since it's a non-calculator exam, the number shouldn't get too crazy with this. And so when I plug in t equals 0, I'm going to have this equality satisfying. So at x equal to negative 1, t equal to 0. And so we're going to plug t equal to 0 here. We have negative of 1, because e to the 0 is 1. 2 cosine of 0, which is 2, minus 1 over 2. So the slope of the tangent, so the slope of the tangent at this point is going to be negative of 2 over 3. And so the tangent line that we have is y equal to negative 2 over 3, x plus 1 plus 1. This will give us negative 2 over 3x plus 1 over 3. And this is my final answer for these questions. So the concept is not that new. It's just this formula of taking derivative of a parametric curve is what important. And so the technique of also guessing the root in multiple choice questions. Next, we'll go into example 3. Determine the coordinates of the points with horizontal or vertical tangent of this parametric curve. And so horizontal tangent, as we define it, so let's first find the formula for dy over dx. This is where you have dy over dt divided by dx over dt. It's where we have, 2t plus 2 divided by negative 1. And so the denominator is always different from 0. We can immediately conclude that dx over dt is always defined. So there is no vertical tangent, because vertical tangent is the one where you have the slope of a tangent going to infinity or negative infinity, and so the denominator have to be 0. But in this case, it's always different from 0. So there's no vertical tangent. Now horizontal tangent is where you have to find the point of t where you have dy over dx equal to 0. And so it's going to be negative of 2. Take the 2 out, you have t plus 1 equal to 0. Or you have t equal to negative 1. And so at that point, we have the xy coordinates be 3 and This is 2t. So it's going to be 3n t squared plus 3 and -1. So that's the answer for this question. So just understand the concept, and it's gonna be the same thing is gonna apply if you were gonna be asked about concavity or area under the curve. Just try to apply the formula that was given. As long as you understand the quantities in that formula, everything should be easy. Now let's go to the last example. Again, if you have any questions when you were watching this video, email me during the week. I'll try my best to answer those emails. Last one, find the values of t such that the curve is concave downward. Now you're given this parametric curves with t divided between 0 and 2 pi. So let's find d squared y and dx squared. So I define it as d over dt of dy over dt divided by dx over dt. And so this one is going to be as we come back to this one, so it's going to be d dt of first one, that one, 2 cosine t, and dx with respect to -3 sine t, and then you take that again, -2 sine t, -3 sine t. So it's going to give us 2 over 3, which is always positive. So the second derivative is always positive, and as we learn in the material midterm 2, it means that the curve is always concave upward with all t between 0 and 2 pi. And so with that in mind, if you have any questions, again, email me. And I have these practice problems at the end as usual. I want to send the slides to Dr. Kasha. Hopefully she's going to upload it on Canvas shortly. But if not, if there's no more questions, I'll see you guys next week. And that's going to be the live session at the normal time on Friday. Have a great weekend.